Hi, welcome everybody. So today I'm going to talk to you about gas laws, what it means to be a gas, what pressure is, and what some of the gas laws are that you should really know about. So, let me talk to you first about what it means to be a gas. And this is something that's known as the KMT, the Kinetic Molecular Theory Model. That's what we're kind of looking at. And one of the first things that you have to know is, well, if I were to draw a gas in a box, what would those particles look like? So if we were to draw that, we would try and draw the particles as tiny as possible and far apart from one another. And this really gets to the heart of the kinetic molecular theory. The first thing is that the particles of gas, they behave as tiny pinpoints. And so the idea is that each particle itself, it has no molecular volume. This leads to a situation where the particles do not exert any force upon one another. So there's no intermolecular forces between the particles, and there's no repulsion between the particles. Now, if you notice in that particular container, there's large spaces. There's large spaces between the particles. And that's important to realize that because of those large spaces, because of those tiny little pinpoints that exist there, because there's no intermolecular forces, the particles themselves are moving in random straight line motion. Random straight line motion. So you have these particles, they're moving in straight line motion, they're tiny little pinpoints. They don't repel, they don't attract each other. There's large spaces between the particles. But sometimes the particles will collide, and when they collide, we say that the collisions are elastic. And when I think about an elastic collision, what that means is that there's a perfect transfer of energy. So the particles, when they collide, they will transfer energy perfectly to one another. And that's important to realize, that the particles, they will not lose energy, nor will they gain energy when they will interact with each other. Now, they call it the kinetic molecular theory. Why do they call it the kinetic molecular theory? It has to do with the temperature behind this. And what we see is that when we increase the temperature, the particles, what they'll tend to do is, particles will collide more often. Not only will they collide more often, but they'll also collide with more force. And when they collide with more force, this will lead to an increase in pressure. This idea of increasing pressure, this leads to a whole host of different things that we see with the actual gas laws, the way that gases behave when we change their conditions. So let's talk a little bit about what pressure is. So pressure, it is a force over area. The unit for pressure, the basic unit for pressure, is a Pascal. And a Pascal is equal to, if we were to break this down into SI units, it would be a Newton over a meter squared. Now, a Pascal happens to be very, very small, and so we don't usually use Pascals. Instead, we'll use a kilopascal, kPa. Now, we could also use other units of measuring pressure. We could use atmospheres. So if we had atmospheres, that's another unit of pressure. We could have millimeters of mercury, which is also known as a torr. And we could have pounds per square inch. These are the most common ones that we see used, especially in chemistry. Now it turns out that there is, like a standard pressure. STP stands for standard temperature, and it stands for standard pressure. And so when we look at this, standard pressure is 1 atmosphere of pressure. It is 760 millimeters of mercury. It is 101.3 kPa. And it is 14.7 psi. And you should know how to convert between these different measurements. So if I give you a unit that is in kilopascals, you should be able to take that and change it into psi, or into millimeters of mercury, or into atmospheres. Now, there's also standard temperature. Standard temperature is 273 Kelvin, or 0 degrees Celsius. If we were doing Fahrenheit, it would be 32 degrees Fahrenheit. Notice I don't put a degrees with Kelvin, it's just Kelvin, it's not degrees Kelvin. Now you'll remember that, when we went back to looking at the volume of a gas, we always said the gas is at STP. And we would calculate the molar volume for that. The molar volume was 22.4 liters. You're going to see why that's the case when we do some of the derivations in the next few videos. Okay, so how do we measure pressure? Well, pressure is measured if we have the atmosphere, the outside pressure, that is measured by a barometer, which I'll show you in a second. And if we're measuring the pressure of a gas sample, we would use a manometer. Not a manometer, it's a manometer. People take for granted that there's pressure that's pushing down on us at all times. We're just used to it. And it turns out that there is pressure pushing down on us, and we can see that pressure with something like this scenario right here. So this is a tanker that was crushed by atmospheric pressure. And the way it happened was the tanker was open, it was emptied out, and it was a hot day, and then they closed up the tanker. There's a valve, an opening, they closed up the tanker, and it was empty, it had air in it, and they left it overnight, and they came back the next morning, and this is what they saw. And so the scenario that took place was inside that tanker, the gas particles started to slow down. But the amount of gas particles was kept the same because it was a closed system. The outside pressure, even though the air got cooler outside, the pressure outside didn't change because it's an open system. So the pressure inside, those gas particles, they slowed down. KMT, the higher the temperatures, the faster the gas. Here it's the opposite. Here the particles, they slow down, they move slower. The outside pressure, it didn't change. So the pressure inside got less. The pressure outside was relatively more. And because of that, the outside pressure crushed this tanker. So here we have a crushed tanker, and we can do this in the classroom on a much smaller scale if we do crush the can, which I can show you in class, and I'll show you that in a second. But how do we measure these types of pressures? Well, first we have the atmospheric pressure, which is the pressure outside, and this is showing you a barometer here on the left. And so using mercury is very sensitive to pressure. We have the atmospheric pressure pushing down on the mercury, and it's forcing it up this tube. And as a result, we can measure the height, and if this was standard pressure, it would go to about 760 millimeters, which is where that unit comes from, millimeters of mercury. If we had a manometer has our gas inside a sealed container, hooked up to a U-shaped tube here. The pressure of the gas is pushing out against the mercury. The pressure of the atmosphere is pushing down on the mercury. We can see there's a difference in height. This height is equal to the pressure of the gas. Now, since this is an open manometer, what you'll notice is that if I put this into an equation, the pressure of that gas is not only the height, but it's also the pressure of the atmosphere. Because the pressure of the gas inside is pushing that much more against the mercury, and it's pushing it against the outside pressure. And so because of that, the pressure inside is equal to the pressure of the atmosphere plus the pressure of the mercury being moved, the height of the mercury. Okay, here's Crush the Can, and I'll do this demo for you. But we have before heating, pressure inside and outside, showing you, like red and blue, the different colors of the gas inside and outside, just to kind of differentiate between them. Red can be considered like, the molecules outside, and blue can be considered the molecules inside. If I heat the liquid, you'll notice that the blue dots increase a lot over here where I just circled. That actually means that there's more evaporation of the liquid. It's getting hot. And then if I cool it down very quickly, those gas particles inside condense. The outside pressure is much greater. Okay, the outside pressure is much greater than the inside pressure. So the inside pressure is much less now that the gas has cooled down. The outside pressure will crush it, and you'll get this pretty dramatic crushing of the can. We can do this in class. You can see what it looks like. So why do we go through all this stuff with pressure, with KMT? The idea is to try and understand what is going on as far as gas behavior. And that is explained by the gas laws. So the gas laws, they are as follows. We can look at pressure and volume relationship. We can look at volume and temperature relationship. We can look at pressure and temperature relationship. And we can look at volume and number of moles in a relationship. These are all the variables that we're going to look at. And so we're going to look at these different variables to see how they relate to one another. Now the way that I wrote these, it's not by accident. They are done on purpose. And so what we'll pick up in the next video is we'll pick up going through how each of these laws work, what their graphs look like, and how to apply them to a problem. All right, thanks so much for watching.